Okay, so hello everyone. I am Seonggeun Park, and as Jung-woo said, I'm electrical engineering senior student at Korea University, and today I am going to present about quantum singular value transformation. Okay, I want to start my presentation by asking a question. You may already hear several quantum algorithms such as quantum phase estimation, quantum amplitude amplification, quantum simulation, linear system algorithm by HHL, uh, and so on. Um, are these primitives truly independent, or can they be seen as examples of a deeper underlying concept? I think it would be fancy if there is a deeper underlying concept. And let me tell you the conclusion first. Yes, there is a deeper underlying concept, and its name is quantum singular value transformation, as known as QSVT. There are a lot of quantum algorithms that have been developed by researchers over the last 30 to 40 years. In the early days, algorithms like Deutsch-Jozsa algorithm, Bernstein-Vazirani algorithm were developed. Then there are the colored quantum algorithms. The red ones are related to eigenvalue estimation. The blue ones are related to Hamiltonian simulation. And the green ones are related to quantum search. However, algorithms are not exactly separated into these categories. For example, LCU is related to QPE, and quantum work algorithm is related to quantum search. And in 2016, the concept of QSP, quantum signal processing, appeared in Low and Chuang's paper, Hamiltonian simulation by qubitization. And it contained the optimal Hamiltonian simulation algorithm. This QSP technique enables optimal Hamiltonian simulation by applying a polynomial transformation to eigenvalue of Hamiltonian. And 2019, the algorithm quantum singular value transformation was created by Gilyén, Su, Low, and Weeb. Not only does it encompass the quantum simulation ideas and quantum search ideas, but also the quantum factoring ideas. That's the topic I'm going to talk to you about today. Okay, before we start talking about QSVT, I'd like to briefly talk about what QPE, quantum simulation, and quantum amplitude amplification algorithms are. I am going to talk about these algorithms, focusing on the problems they are trying to solve. Okay, first of all, quantum search. You may be familiar with the name Grover's algorithm or quantum amplitude amplification. This algorithm is solving unstructured data search problems. Given X in 0 to 2 to the n minus 1 and the oracle S omega, we have to find omega. And the oracle, we have flipped the phase if the input is the target state, omega state. And how can we solve this problem? Let UA be any quantum algorithm and the state psi is equal to UA applied to zero state. And let's assume that the inner product between the target state omega and the initial state psi is equal to C, which is not zero. The inner product value would be very small if the data structure is huge. Then we have to amplify the C by applying unitary evolution to our initial state psi. I mean, C is the inner product between our quantum state and the target state. If C becomes approximately 1, then the measurement outcome will be the target state with high probability, right? And the method to amplify this C is quantum amplitude amplification algorithm. Okay, then quantum simulation. if there is given Hamiltonian H, Hamiltonian simulation algorithm make unitary operator, which is sufficiently close to exponential minus IHT. Quantum phase estimation is the last example, but not least. The problem that quantum phase estimation to solve is given unitary operator U and its eigenvector X, estimating the eigenphase of the unitary operator and eigenvector. At first glance, you can think that quantum search, quantum simulation, and quantum phase estimation seem very different. Okay, then I'd like to define singular value transformation in this section. And before talking about singular value transformation, I'm going to talk about singular value decomposition briefly. Okay, SVD, singular value decomposition. All m by n complex matrices can be decomposed by two unitary matrices and one diagonal matrix, like this. A is equal to W, sigma, and V dagger. W is an m by n unitary matrix, and it contains left singular vectors. And V is an m by n unitary matrix, and it contains right singular vectors. And we can make the diagonal term of the sigma is non-negative real number, and the diagonal elements are called singular values. SVD can be applied to any matrix, including non-scalar matrix. Generally, SVD is hard to compute for large matrices. And you can see the picture on the right side. The linear transformation A can be decomposed by 3 steps: rotating by V dagger, squeezing or stretching by sigma, and one more rotating by W. Quantum gates in a quantum circuit are all unitary gates. However, we sometimes have to use general operators rather than unitaries for purpose such as applying non-unitaries to a quantum state. This slide deals with how to embed a general operator into a unitary operator. Let's define the matrix A as the product of two orthogonal projectors, pi tilde, pi, and unitary U, such that A is equal to pi tilde times U times pi. And we call U unitary embedding of A, pi tilde, left singular vector space projector, and pi, right singular vector space projector. A special case of projected unitary encoding is called block encoding, when pi tilde is equal to pi equal to 0, tensor I. There is a terminology, alpha A epsilon block encoding of A. And you can see the definition of alpha A epsilon block encoding of A in this orange box. Suppose that A is an S qubit operator, and A and epsilon is positive real value, and then then the S plus A qubit unitary U is an alpha A epsilon block encoding of A if the difference between A and this alpha zero bra vector tensor identity U zero cap vector tensor identity is less than epsilon. And you can represent this block encoding on the top left corner of the unitary, like below. And we use the same notation for the general unitary embedding. this is just a convention, and you can write A on the top left corner of the unitary, even though the projector is different with projector of block encoding. So this is summary of SVD and unitary embedding of a matrix. W sigma V dagger is SVD of SVD result of A, and U is the unitary embedding of A. If we denote left singular vectors by psi I tilde or Wi, and right singular vectors by psi I or Vi, then we can write A as summation of the product of singular values and its corresponding left singular vector and right singular vector, right? And this is time for defining singular value transformation. I said that A is equal to this. A is equal to sigma and sigma I, psi I tilde, and psi I. Then we can define the polynomial singular value transformation of A. Look at the orange box. For all the function f, fa would be sigma, f singular value, psi I tilde, and psi I. And for even polynomial f, fa can be defined as sigma f singular value, psi I cap vector, and psi I bra vector. The difference between the odd function and even function is the cap vector, tilde, and there is no tilde. And these are our main theorem. Let's assume that there are given U, pi tilde, pi, such as A is equal to pi tilde, U pi. The first box, theorem QSVT, said that each plane defined by a common pair of left and right singular vectors can be manipulated independently as if like separate SU to qubits and without computing SVD. And the second box, theorem QSP, quantum signal processing, said that its singular value can be transformed by any arbitrary polynomial. By combining these two theorems, we can conclude that we can transform singular values into any arbitrary polynomial independently. So I mean, it means that when we do manipulating, there is a way that different singular value does not affect each other. Okay. So then let's go back to quantum searching, QPE, and quantum simulation. There are 3 algorithms like this, and let's look at the quantum search first. Psi 0 is our initial state, and omega is our target state. And UA is an arbitrary quantum circuit. Then omega cap vector, omega bra vector, UA, psi 0, have one non-zero singular value. If we assume that singular value C, and it is, we can assume that C is not 0 and C is the singular value. Then by applying sine function on the left side, and we can, by applying sine function to singular values C, then we can apply C to 1. And there is some dashed line on the graph of right side. And that dashed line means polynomial approximation of sine function. So generally, C cannot be amplified to exactly 1, but we can adjust the maximum error denoted by epsilon. there is a trade-off between epsilon and time complexity. Secondly, QPE. By applying QPE algorithm using QSVT formalism, we have to use 1/2 I plus exponential minus 2 pi I phi u to the 2 to the j power, like this embedding. And we need to apply the function you can see on the right side. QPE using QSVT is a little complicated, so I am not going to talk about it precisely, but the intuition of this algorithm is using iterative quantum-based estimation instead of the basic QPE. Thirdly, quantum simulation. In quantum simulation problem, we assume that we already have block encoded Hamiltonian, and we have to convert its singular value, or I can say eigenvalue here, energy to exponential minus I energy t. And to convert energy to exponential minus I energy t, we need two real functions, cosine function and sine function. And you can see two functions on the right bottom side. And from now on, I want to talk about our main theorem more precisely. Okay, quantum signal processing. I mentioned a simplified version in the previous slide, and I want to define precisely the theorems. Suppose one can apply a gate sequence, RZ gate, RX, rotation Z gate, rotation X gate, rotation Z gate, alternatively, and where zeta is unknown, but we can control the angles phi 0, phi 1 to phi k. And some people called this rotation X gate as a signal gate, and rotation Z gate as signal processing gate. So you can think that zeta is unknown value and it is signal, and we can process this signal using rotation Z gate. Sorry. Which unitary operator can we build this way? And okay, before to answer that question, I want to slightly modify parameterization and define Wx like x, I square root to 1 minus x square, and I square root 1 minus x square, and x. And this is equal to exponential I arc cosine x sigma x. Then, by setting x is equal to cosine theta, the equation above can be written as the alternative multiplication of RZ gate and WX gate. And you can, I want to explain the quantum signal processing theorem. Okay, there exists, this theorem says that there exists phi, a set of angles, phi 0, phi 1 to phi k, such that like this alternative multiplication of rotation Z gate and WX gate, we can make polynomial encoding. A polynomial block encoding unitary. Encoded unitary. So if and only if degree of P is less than K, P has parity, K modulo 2, K modulo, this second condition means that if K is even, P has even parity, and if K is odd number, P has odd parity. And all X to -1 to 1 px, the magnitude of px is less than 1, and there is two more conditions. So this quantum singular processing theorem says that you can build a px polynomial by applying a rotation g gate and wx. You can build polynomial by alternatively applying rotation z gate and wx gate. And the algorithm that finds phi to implement p needs O to k to the 2, k square arithmetic operations. And I want to put Rx instead of Wx. So first, I have to define the Rx. And we define a parameterized family of single qubit reflection operators for all x from -1 to 1, such that looks like this. Rx is equal to x square root 1 minus x square, square root 1 minus x square, and minus x. And there is, and the second box said that the second box means that a slightly a modification of the theorem of the previous slide, which use Rx instead of Wx. And we can call this as quantum there is typo. Quantum signal processing using reflections. And okay, then let's move on to QSVT. Recall that A is equal to pi tilde U pi, and its SVD is, the result of SVD is A is equal to W sigma V dagger. For each singular value, sigma I, a plane is defined by VI perpendicular in the image of the projector pi. And a matching plane is also defined by WI and WI perp, which is in image of pi tilde. U is rotation on this 2D plane, VI perp to WI perp. And let's look the orange box, the definition of alternating phase modulation sequence. Let phi, that phi is the sequence of real value, length n. Then we define the phased alternating sequence u phi as follows. So there is a slight difference between n is odd case and even case. Then I told you in the previous slide that PA, polynomial transformation of A, is equal to P pi tilde U pi, and it is equal to, like, if the polynomial P is odd, it is sigma P singular value I, psi tilde and psi I. And if polynomial P is even, it can be defined as sigma P singular value I by psi I and psi I. And so this is our main topic, the theorem of quantum singular value transformation. Let P is a polynomial which have complex coefficient, and phi is the sequence of real number with length n, is as in theorem quantum signal processing using reflections. So this phi is equal to this phi I mentioned when I talked about this phi when I talked about quantum signal processing. Then you apply the same phi and making the u phi. Then you will get PA. So polynomial transformation of matrix A. So PA is equal to P polynomial of pi tilde U pi. And you can get the polynomial transformation, singular value transformation by using U phi. And what is the time complexity of this quantum singular value transformation? So if we want to apply the polynomial of nth order, then we need the length, the phi, which have length n. Then the alternating phase sequence U phi can implement it using a single ancillary qubit and uses of U and U dagger, and n uses of C pi naught, and n uses of C pi tilde naught gates, and n single qubit gates. Okay, let's look at the example of using QSP and QSVT. And I will explain about the example of a linear system developed by HHL and quantum simulation and fixed point amplitude amplification. So first, how can we explain fixed point amplitude amplification by using QSVT formalism? So before talking about fixed point amplitude amplification, I want to talk you about the original quantum amplitude amplification, and the original quantum amplitude amplification can overcook the quantum state because if you can see the picture on the left side, your initial state is psi, and if you and you can think the Grover algorithm, and if you apply Grover operation to your initial state, and that your initial state evolution to cube psi, and cube psi is more near to our target state omega. But if we overcook our quantum state, then our quantum state does not contain enough portion of omega state, like this q to the 5 order of 5 psi. And how can we avoid overshooting yet still have fast O to the scale to n search? And the answer is use Chebyshev polynomial for phases. And so you can see the graph below, right side. There is some oscillating graph, oscillating line with black color, and it is the original amplitude amplification. And you can see purple or blue line, which have, if they are closer to 1, even though we apply quantum gates again and again. So this is fixed point amplitude amplification. And I mentioned that the table above, and yeah, the sine function, if you can say that if we apply sine function to a positive number, and that positive number become 1. And we can use this idea to do fixed point amplitude amplification by QSVT. So The theorem, fixed point amplification by using QSVT, is in the box. So let U be a unitary and pi be also going to projector such that A omega is equal to pi U psi 0 and A is bigger than delta and delta is bigger than 0. There is a unitary circuit U dagger such that omega minus the norm of omega minus U tilde psi 0 is less than epsilon, which uses a single Ancela qubit, and the number of gate we need the number of U tilde C pi naught and C psi 0 psi 0 naught and RZ gate is proportional to log 1 over epsilon over delta. Okay, then quantum simulation by QSVT. We use the Fourier-Chebyshev series of the trigonometric functions given by the Jacobi angle expansion. So we can make cosine and sine by using Bessel function and Chebyshev function. This Z means Bessel functions and T denotes Chebyshev polynomial. And we can truncate it because in real situation, we cannot apply the order of infinite. And we can combine this cosine and sine function by using the concept of LCU, like this. Then we can get exponential minus I Hamiltonian T. And lastly, HHL by QSVT. So HHL is the algorithm for linear system, and we have to construct the inverse matrix of given matrix A. Then we can choose phi to give polynomial, which is 1 minus sigma squared to the power of B over sigma. And it is called Moore-Penrose pseudo-inverse. And if B is sufficiently large, we can use it as 1 over sigma. And you can see the graph of that function. So we can use this function to convert our singular values to inverse. Okay, so the conclusion. So QSVT unifies major quantum algorithms, example like quantum search, Hamiltonian simulation, linear systems, under a single framework. And QSVT allows efficient algorithm design by leveraging problem structure, and QSVT offers a flexible and intuitive parameterization, enabling the discovery of new quantum algorithms. So this is all, and the references are below. So thank you for listening, and if you have any question, feel free to ask me. Thank you.